Hello everyone, in this video we are trying to learn about linear regression in auth engine. So linear regression is the method of predicting some variables using other sets of variables. So we find the relationship between two different variables and try to predict using one of them to know the other. And in auth engine we have different functions for that. So we have different functions. The first one is ee.reducer.linear fit, and similarly we have ee.reducer.linear regression, .robust linear regression, and .rich regression. So for understanding the linear regression, we certainly need some concepts of linear regression, but the objective of this video is to go through the course and try to see or try to know how these linear regressions are applied, and hopefully we will try to learn some of the concepts of maybe concepts of linear regression as well. So in the first set of course we are trying to apply this linear regression in the image collection. So here we have the very first function, and this function takes the image, adds the bands, returning the time property to the image. So from the metadata we are selecting this time property, we divide with certain constant and add to the image as the new band. So this is the very first function, and then we use this data set here. This is some data that projects the climate data as far as to the end of the century, and there are different scenarios for that. Here we are using RCP85. There is also something called RCP45. So let's understand that there are different scenarios, and different scenarios have different ways of projection of the climate data. And after filtering the scenario, we are filtering the dates, and here we have the dates starting from 2006 ending 2050, and we add this function by .map, and this creates a new time band to this image collection. And from that image collection we're selecting the time properties, which is the independent variable, and then we have this PR_mean. This refers to the precipitation, and we are selecting this as the dependent variable. And here we are using it by ee.reducer.linear fit, before which we have .reduce. So we are applying the very first function here, .linear fit, and this gives us some result. So we have this scale and offset. These are the results, and we can display the result. So we will see what happens a little later. And then again we are creating here the time band in the second quotes, and we also are creating this constant band to the image. So this is done by e.image, one inside the parenthesis, adding the bands to the image. So this creates a constant band to the image. And then we have the same process of doing this. We are selecting the scenario and we are filtering it by date, and then we are adding these two different functions by .map, and this creates a time band and the constant band. And again we are selecting the different variables as the predictors and the responses. So here we have the constant time property. We have here PR_mean. This is precipitation, and here we have the TAS max. This is the maximum temperature, which is the projected up to here we have the date up to the end of the century. And then we apply this list square regression by ee.reducer.linear regression, and this computes coefficients. And here we have the we are providing the numbers as the number of predictors and the number of responses. And we can also use that next function, that is ee.reducer.robust linear regression. So we can find the results and the results are has something called array images, and that must be flattened. In other words, we want to make them easily retrievable, and here we are selecting the coefficients from that variable or the computation before, and we take the band names and flatten it. So here we are repeating this process for two different regression, and we can add them as the layer. And for comparing the results, we want to get the results at the specific point, so we are getting the very first result from that specific point, and we can run this and see what really happens. So in the first case, we had this result applied as the bands, so it gives some sort of colors, and here we have the minimum to maximum values, and the colors are not appearing for now. Let's see this one here. So we have the first estimates here. So we have here the different computation from the regression. So here we have the different computation. So we certainly need understanding of the linear regression to understand what's being resulted. But this is the way that we have computed, and we have retrieved those results. So in the first case here, we had the image displayed. So to interpret this one, so we have the increasing trend as the blue one, because the value is 1. So the blue areas means that it has the increasing trend, and the decreasing trend is in red color, and the areas which is green, there has been no trend, or there will be no trend. So this is the way to use this output in the image display. So there is also the application of this linear regression in the image as well. So here we have our area of interest, and then we have the image. We select the band 5 and band 6. Band 5 as the independent variable, and band 6 as the dependent variable. And then we calculate the regression coefficients by dot reduced region, and then we apply this reducer ee.reducer.linear fit, and we retrieve the results. So the first one is linear fit, then we get the offset and scale. So these are the terms used in linear regression, and we can print them out, and these are the let's say the relationship between two different variables, independent and dependent variables. And again, here is a second set of codes. We have the area of interest, we have our image, and we are selecting the band 5 and band 6, and we also add this constant band, and we group it by e.image.cat. This .cat groups the image or concatenates, and we can calculate the regression coefficient by dot reduced region, and applying this reducer as ee.reducer.linear regression. So we have the num_y set as 1, as there is only one dependent variable, and we have 2 number here for as we have the 2 independent variables. And then we have the geometry, our area, we have the scale, and for getting the results, we want to convert the coefficients array as a list. So this is done by e.array. So this is our array, and we get them as the list by .toList. So here the one thing to note is that we need to have the understanding of arrays and lists, so we can play through them as well. So we get the y-intercept by this dot get. So from that list we get the first value as the y-intercept and the second one as the slope. And for extracting the residuals, we have the dot get residuals. This is again as the array, and this array is converted as the list, and from that list we get the first value. They are the residuals, so we can print them and see what really results. So it's taking time, I guess. Okay, so here we have the results being computed. So we get some sorts of numbers here. So here in the very first one we had the linear feet printed. So this gave us offset and scale, and from that one we selected the y-intercept, that is the offset, and we had the slope, which was the scale. So different terms here. And we also had the here for the second sets of codes we had this coefficients and residuals. We had the y-intercept printed, and then we had this slope and some residuals. So this is the way to do the linear regression in the images in Earth Engine. Similarly, we can do this in the feature collection as well. And here we have the signal to image, then we have the landscape image, and we are converting those two images as geometry, and we find the intersection region between these two images. And within these two images we find the common area, and from these dot random points we want to find the random points, 1000 random points within the area which is the common area. And we also select the band 11 and band 6. We add them as the bands, and then we rename those two selected bands. So we are only selecting this shortwave infrared bands from two different images. And after selecting the bands, we sample the regions. So this dot sample regions selects the point and provides the values in that point. So basically what we're doing is to those 1000 points here, in every 1000 points we provide the shortwave infrared one and landscape shortwave infrared one. So two different shortwave infrared bands value will be stored in those 1000 different points. So this is what this dot sample regions is doing. And we also add this constant to be used as independent variable, and here we are computing the regression coefficient. So this is done by dot reduce columns here, and reducer is ee.reducer.linear regression. So the numbers means that we have two different independent variable and one single dependent variable. And we select the constant, we select the two different shortwave infrareds here. And to convert the coefficients array to a list, we again do this by e.array. We get the coefficients, and this is converted to as the list by dot to list. So we can see what this results, and we can also get the y-intercept. So this is what we did in the previous one. So we are getting this as the list, and we get the y-intercept and slope. And we want to have selections of those two different values. So here we have the reduced columns, and we are getting them as the list, and we are selecting props. So this gets the different values from all the values from the S2 shortwave infrared and LH shortwave infrared. So we get them as the list, selecting the first value and receiving them as the array and the both of the process. So why we are doing this is we want to do the calculation as we do in linear regression. So from those received slope and coefficients, we want to predict the variable. So for this we are getting this array here. We're mapping the function, and we have this number. Each number will be multiplied by some slope, and integer will be added. So this is done because we want to predict based on those received values. And here we have the e.array.cat to group all those variables, and this this variable is now used in ui.chart.array.values and plotted as the scatter chart. So let us run this. So this whole process here was done to get this scatter plot here. So to revise again, we have this two different images. We get the common area. From those area we had we selected 1000 points randomly, and we provide the unique values to those 1000 points, and from those 1000 points we also added the independent variable, and we do the reduced linear regression, and then after we get the linear regression, we get the coefficients converted as the list, and we had the y integer and our slope. And not only that, we want to predict from those extracted y-intercept and slope to predict the our dependent variable. So this is the whole process of doing that one. I try to explain, and finally we plot the chart of ui.chart.array.values, and we see this line passing through both of them. And we also can apply the linear regression in the list as well. So we have the variable column here. The first one is the independent variable, and the second one as the dependent variable, and then we reduce it by ee.reducer.linear fit, and we apply this ee.dictionary so that we can get the results easier, and we can print them. So basically this is the finding of the relationship between two different values. We can provide our own numbers, of course, and see what happens. Similarly, we can also have the three different columns here. So the first one here is the constant term, the second one as the independent variable, and the third one as the dependent variable. And we can do this by ee.user.linear regression, and this is converted as ee.dictionary for making the easy access of those results. And here we have num y as 1 because we have single dependent variable, and 2 as 2 because we have independent variables as two different independent variables, and we can convert them as the list. So we get the result as e.array, and then we convert them as the list. We get the y-intercept, and we get the slope here, and we can print the residuals as well by getting the residuals from that variable, converting them as the arrays, and that array is converted as the list, and the first value is retrieved. So we can print them all. So here in the first one we had this linear fit, we had some values here, y-intercept as 0 and slope as 1, and we also have this one here, printed coefficients and residuals. And this is how we conclude this video. So basically I tried to explain the process of applying this method of linear regression in our engine. So basically we try to see what really happens in this process, but more understanding is certainly required in understanding them and understanding the output. So I hope this was helpful to you at some extent. Thank you for watching.